Oh, Detta, we got to example 5, but basically we said this. As an equation, the law of conservation of energy said the potential energy you start with plus the kinetic energy you start with has to equal the potential energy you end with plus the kinetic energy you end with. The amount of energy you start with has to equal the amount of energy you end with. I think I had said show marble energy transfer device, and then I found to my chagrin that over Christmas it had been nudged, so I fixed it. Here we go. I gave the marble some potential energy. And slowly that potential energy got turned into not just kinetic energy of the marble moving. Could you hear it? That was some energy. And you saw these things move. This one's still moving. They stole some kinetic energy. That's why the marble, when it got here, was traveling slower than if I just dropped it. If I just dropped it, all of the kinetic, so all the potential goes into kinetic, the energy of motion. But it lost some energy along the way to other dissipative forces. We did a couple of questions where we said, actually we could have used kinematics, but where conservation of energy really shines is roller coasters. And so we got to example 5. I like example 5. I like example. There's going to be a roller coaster on your test on Wednesday. And Maxine, the test is going to be Wednesday. In fact, there might be more than one roller coaster. Who knows? Okay. Roller coaster car travels as shown below. At point A, it is moving at 12 meters per second. Page, what does A want me to find? Part A want me to find? When it reaches, what does it want me to find? Yeah. Oh, thank you. Page, I was worried you were going to say velocity. You said speed. Good, because we are going to find it with a scalar. How fast? And I'm going to assume if you're a roller coaster fan like me, yeah, that's what you want to know. How fast am I going at the bottom? Page, is there a change in height? Is there a change in speed? Yeah. Is there a yucky, curvy path? That's a job for conservation of energy. Okay. Cool. So let's write down the law of conservation of energy. It's on your formula sheet. It goes like this. On the formula sheet, did I start with KE initial or PE initial? It doesn't matter, but, sorry? P, okay. So PE initial plus KE initial equals PE final plus KE final. Paige, can you read to me the first 4 words of part A, starting with the word if? If they had said include friction, don't write this down, I would have said plus heat, but they said ignore friction. Okay. Then we always ask, are any of these zeros? Where will kinetic energy be 0 when we are at, looking for where that starts with the letter R? When we're at rest, because kinetic energy is the energy of motion. At the top, are we at rest? No. At the bottom, right? 12. At the bottom, are we at rest? By the way, you know what we should do? Alex, let's go initial, let's go find, there, now we know what we're talking about for our, put an I and an F there, right? A and B. At the bottom, are we at rest? No, in fact, you know what? Paige, when I find how fast here, is the answer going to be bigger or smaller than 12? You go slower at the bottom of a roller coaster than at the top? Okay, and I'm glad you caught yourself because you made a guess and then you went, wait a minute, no. So we have a bit of built-in error check if we make a typo in our calculator and I get 8. No. In fact, probably a fair bit faster, but who knows? Okay. It's not quite as easy because of that squared. I can't simply say, twice the height, twice as fast. It's not that easy. There's that squared gums things up. So is kinetic energy ever 0? No. What about potential energy? When is potential energy 0? When we are on the? Yep. Gone. Yes? Okay. mgh initial plus a half mv initial squared equals a half mv final squared. Paige, do you like roller coasters? Kind of. Have you gone on a roller coaster before? Before you got on the roller coaster, did they make you step on a scale? Did they have to spread everybody out to make sure all the masses were all balanced? Could little kids and grown-ups go on the roller coaster? Why? Is there an M in there? Is there an M in there? Is there an M in there? Is there an M in everything? Mass cancels. So even though this question gave me the mass, by the way, if you don't cancel the mass, if you're not sure, you can leave it in, and anywhere that you, if it does cancel, anywhere that you multiply by 245, later on you'll divide by 245 and you'll still be okay. So if you're not sure, leave it in. But I'm enough of a nerd that because I know it does cancel, I can't do extra writing if I don't need to. So they gave me the mass even though technically they didn't need to. Paige, what are we trying to find? Which one, initial or final? Yep. Okay. I want to get that by itself. Ooh. I'm going to do a clever trick. Alex, what's in front of the VF squared? What's in front of this VI squared? There's not a 1/2 here, but here's a clever trick. I'm going to clear fractions. You actually learned this in Math 9. I'm going to times everything by 2. I'm going to multiply by 2, multiply by 2, and multiply by 2. You don't have to do this trick, Louise. If you wanted to, you could divide by 0.5 square root and you're done. But I want to show you something kind of cool, because what happens then is this. That 2 and that 1/2, they cancel each other because half of 2 is 1. This 2 and this 1/2, they cancel each other because half of 2 is 1. Here, I get a 2GH initial, just drops down like a domino, plus VI squared. And then Paige, if you don't mind, instead of writing equals VF squared, can I put the equals and the VF squared on the left where we're used to seeing it by itself? Hey, this looks kind of familiar. Do you recognize it, Maxine? Ready, ready, ready? Here's how I taught it to you way back in October. Look up. VF squared equals VI squared plus 2AD. Is that an acceleration? Yes, it is. Is that a distance? Yes, it is. That equation from way back when in October, VF squared equals VI squared plus 2AD, it's a consequence of the law of conservation of energy. So I don't know if you remember, I told you I would show you the proof for that one later. Here it is. There, it just showed up. Is that all right? Kind of cool. Paige, I got a VF squared. I want a VF. How do I get rid of a squared? The whole thing. So it's going to be this whole thing inside a big square root. Okay. It's going to be the square root of 2 times 9.8 times 18 plus 12. Don't forget the squared. I know the answer is bigger than 12. What do you get? I think you forgot to square root, because if a roller coaster is going 4,000 meters per second, as much as I love roller coasters, I'm not standing in line for that one because I want to live. 22.3? Is that right? Is that any good? Can someone multiply that by 3.6? How fast are we going in kilometers per hour? Sorry? That's not bad. I'll stand in line for half an hour, 45, but not for 3 hours. I have stood in line for 3 hours for one coaster. It's called X. It's at Six Flags. You're mounted on the sides of the track, and so they can, anyways, it's really cool. Well worth it. As far as I'm concerned, for a roller coaster, I can ask you to either find the initial height, the initial speed, or the final speed. You can get any of these by itself. And although it looks intimidating, because it's VF squared equals VI squared equals VI squared plus 2AD in disguise, you've already had plenty of practice getting any one of those by itself without really realizing it that you were practicing. Suppose the coaster is only traveling 15. We have a radar gun, a radar detector, and we measure it at 15 meters per second, not 22.3. How much energy was lost to heat? Jay, what does this want me to find? This is also a job for conservation of energy. How can you tell? Energy lost for heat, and there's a yucky curvy path and a change in height, a change in speed. I'm going to do conservation of energy, GG, except I'm going to add heat. So it's going to be the initial plus the initial equals the final plus the final plus, I guess, whatever's missing went into heat. We can still say this, because we're still on the ground. We're not starting at rest. We're not ending at rest. We're not starting on the ground, so nothing else is zero. Jay, what am I trying to find? How would I get the heat by itself? How will I move the KE final over? And this is the weird one that for some reason a lot of kids want to divide, and I don't know why. Yes, subtract. You are correct. So, Jay, I think it's going to be the KEI drops down like a domino. The PEI drops down like a domino. Minus the KEF. And then, if you don't mind, I'm going to put the heat by itself over on the left-hand side. I'll even do it in red, because heat. Hot fire. So the heat is going to be a half mv initial squared plus mgh initial minus a half mv final squared. Is that right? There you go, Mesa. Is that right? Jaya, is there an M in this last term? Is there an M in this term? Is there an M in this term? Is there an M hiding in heat? Say no. So do the M's cancel this time? So Paige, I lied to you a little bit. In real life on roller coasters, the masses don't cancel. But here's what we do. We grease these coasters down so there's very little friction, so that heat is really, really small. It's negligible. And an empty coaster will make it through in the same way a full coaster will. There's plenty of safety on either end. So I fibbed a bit. In a perfect frictionless roller coaster, mass does cancel. In our real world, it doesn't, but that's what grease is for. Heat is going to be 0.5. Jaya, what was the mass? What was the initial speed? 12? Don't forget the squared. Plus 245 times 9.8 times 18, yeah? Was the initial height? And then minus 0.5 times 245 times 15 squared. Mr. Duke, why didn't you put 20 or what? Yeah, what 22.3? Because they told me actually that's how fast we were going, not the theoretical speed, but the actual speed. How many joules of energy did we lose to heat? That looks like a 98, 9.8. You get 33,000. If I go to 3 sig figs, 33,300, or am I wrong? Anybody nodding? I see one nod. I see two nods. I see three. Okay, good. 33,300. Joules of heat. If you didn't get that, check your squareds, and then check to make sure that you minus that last term instead of added it. What's your homework? So can you all take a look at number 1? Mesa, leave your calculator for a bit. Can you all look at number 1? Number 1 says calculate the potential energy. That's going to be mgh. The kinetic energy, it's going to be half mv squared. Mechanical energy, velocity, and height of the skater. Mechanical energy is just potential plus kinetic. All right. So let's look at example 1 here. In location 1, what's the potential energy as a number exactly? How do you know? So 0. What's the kinetic energy? A half mv squared, whatever that ends up being. What's your mechanical energy? Potential plus kinetic. In this case, 0 plus whatever a half mv squared is. And that mechanical energy, that's going to be your total energy. That's like, remember the skate park video or app I showed you last day? That yellow bar that never changed. So that number will be the same there. That number will be the same there. And from there, you should be able to subtract your way and figure out how much each of these, or how big each of these needs to be. Here they gave you the height, so you can figure out the potential energy, calculate what's left over for kinetic. Here, what's V final? 0. So I can tell you the kinetic is 0. So I should be able to figure out how much its potential, what the height is. So there's number 1. Number 2 is very, very similar. 3, also a roller coaster, looking at it on the side. 4 is good. 5 is good. 6 is good. 7 is good. So Mr. Dewick, you assigned every question? I did. What I'd like to do is, right now it's 12:37. At about 1:15, I'd like to do another lesson. I'll give you a half hour to work on this, and then we'll finish off the unit, okay?